Hello and welcome to our discussion on Zumdahl chapter 11, the first few sections, properties of solutions. So to begin, let's define a solution as a homogeneous mixture of gases, liquids, or solids. Homogeneous is the key word, appearing of one phase or one set of properties. So if you see two unique properties to things in the solution, it's not a solution. A saturated solution contains the maximum amount of solute at a given temperature, and essentially what you have at that set of conditions is equal rates of forward reaction, which would be dissolution, and reverse reaction, which would be formation of crystals. So the solute particles are dissolving and recrystallizing at equal rates when it's a saturated solution. You and I, from outside the container, we see a clear solution, typically clear anyway. Unsaturated solutions contain less than the maximum amount, and therefore more dissolution can still take place. So as the solute is added, it dissolves completely, and more can still be added in. A supersaturated solution contains more than the amount that the solution should be able to dissolve at that certain temperature. A supersaturated solution is very unstable. In the addition of a seed crystal or agitation or vibration can cause excess solute to crystallize out of the solution and leave behind a saturated solution. Of course, keep in mind that often the recrystallization process may be endothermic or exothermic and change conditions. So, important to keep it. A saturated solution is an equilibrium system. This is very important. And this is an image that emphasizes that, is that you're seeing crystallization and reformation of solution at all times. How do you make a supersaturated solution? People often think, well, you just add more solute. The problem is that it doesn't dissolve without some reason to. So you have to do what happens here. And so we're going to kind of track along this process. Imagine we have a substance that weighs 91 grams can dissolve in 100 milliliters of solvent. We don't know what it here is, doesn't really matter. If we start off by just dropping it in water, and we see that initially 5 grams dissolves without any sort of help, and we stir, and we reach a dynamic equilibrium at that 91 grams. 9 grams is still undissolved in the bottom of the container. If we add a little bit of heat, there's our delta, we can get all 100 grams to dissolve in solution at 50 Celsius, which is, again, changed our conditions. And so we're now unsaturated at a different temperature. If we allow the system to cool slowly, we can get back down to 25 Celsius without that 9 grams forming crystals immediately. And there has to be some sort of impetus for that to happen. Now, some systems are easier to supersaturate than others, and that gets into the dynamics of the properties of the things involved in the crystals, and that's more for advanced chemistry. But for us, we need to understand that this can happen. And then at some point, if we add a seed crystal, which means we take a little crystal of our solute or some other substance and drop it into the solution, we will see this amount that is supersaturated recrystallize and fall to the bottom of the container. Again, I said you can do this with agitation sometimes, and you'll find commercial products that contain sodium acetate have a little snap mechanism inside a bladder full of a supersaturated solution of sodium acetate, and then just snapping that little metal disc will create supersaturation, or will create crystallization, which in that process releases energy for that particular reaction. So talk about molarity. Molarity is moles of solute per liter of solution. Very important. We are not discussing molality. If you see molality, you know it, but it is moles of solute, kilogram of solvent. It's a little different. Don't need to know that though. Just it's not a misspelling. It's just molality. Mole fraction we've studied before is simply the number of moles of a given substance of a solution divided by the total number of volumes in the system. This can be done for a gaseous system or an aqueous system, but the target is on top and the total number of moles of things in the system are below. Notice it's a fraction, not a percentage. Don't multiply by 100. So here's an example question. Hydrogen sulfide gas has a solubility of 0.35 grams per 100 milliliters of water, 20 Celsius in 1 atmosphere. Calculate the mole fraction of the solute and the solvent in a saturated solution of hydrogen sulfide and water under these conditions. Because they didn't give us a volume, let's just assume 100 milliliters. the volume of our solute of a gas is going to be negligible. So you can assume density of water, um, and given a question on a future any sort of assessment, you can expect that you will be able to. You'll be. It's just the question will tell you whether you can neglect the volume change. Anyway, so there's our density of 1. Then we're going to simply find out how many moles we have of the hydrogen sulfide by the molar mass. Then we do the same for the water. And assuming these are the only 2 things in our solution, then we have our mole fraction of hydrogen sulfide divided by the two added together. And then finally, the mole fraction of water. And those, of course, should add up to 1, and they do. And we're done. That's pretty quick and easy. Let's talk about the energies of solution formation. This is a kind of a hot topic in AP chemistry right now because it's just hot. Things get hot. The energy of dissolution of a solute in a solvent depends upon the strength of 3 different attractions, as well as the change in entropy of the system. These 3 attractions determine the overall heat of solution. First is the attraction of solvent particles for each other, or the delta H of the solvent. Of course, this value will be higher in polar solvents and lower in nonpolar solvents because polar solvents contain attractions like dipoles, hydrogen bonds, whereas nonpolar solvents, the only attraction there is LDFs, and if it's a liquid, your molar masses aren't going to be that great. So this is an energy that must be overcome if we're going to make a solution. So this is energy input. Okay, so delta H is going to be positive for this. This is sometimes referred to as expanding the solvent. The second is expanding the solute, which is delta H of the solute, or the solute particle attractions for each other. It's very high in ionic and polar solutes and low in nonpolar solutes. Very endothermic, requires lots of energy, so this one's going to be also positive. This is an energy input. We must overcome this attraction. Remember, we're starting with water, which is a solvent. Number 1, we're just assuming water. And now we're talking about the solute we drop in. Could be sugar crystals, could be salt. The delta H of the solute is equal to the opposite of the lattice energy. Okay, so if we know the value for lattice energy, we turn the sign positive and we have delta H of the solute. Now this is true for ionic compounds. If your substance you're dissolving is not an ionic compound, then there will be some other value, possibly a lattice energy. It may go by some other name. But the bottom line is you need to know how much energy it requires to turn the particles you're dealing with into the gas form. Why the gas form will come up a little later. So the third thing we have to think about is the attraction of the solute particles for the solvent particles, or the delta H of the mix. I'm using the term mix because it's clearer what we're talking about. We're allowing this to form ion in case of water and salt, for example. Ion dipole forces of some kind. The ion would be coming from our, assuming an ionic solid, the dipole from water, if water was our solvent. So we're coming up with a new force, a new attractive force. Whenever we form a new bond, that's going to release energy. So the attraction for solute particles and solvent particles is high and negative in nonpolar solvent, polar solute solvents, and lower in other conditions. This is energy output, so it's going to be a negative value. And sometimes this is called forming the solution. So we had go back to it, expanding the solute, expanding the solvent, and then forming the solution. The first 2 were positive, and this one is negative. So you can imagine we have to input energy to break the bonds of the solute. We have to put energy to break the bonds of the solvent, and then producing our solution will release energy. The difference here will be our delta H of solution. It could be positive or negative. It depends on the system. So here it is, another graphic. We have expanding the solute, expanding the solvent, formation of the solution. These 3 values all together make delta H of solution, and here's that card. So delta H of solution is the enthalpy change associated with formation of a solution. So imagine you have a solute, and then you have a solvent, and you put them together, and you measure any temperature change that happens above or below room temperature. That's your delta H of solution. So we're explaining the dynamics of pulling apart the solute and the solvent and the energy released when the solution is formed. It can be positive or negative, depends on the system. Another value that's often described in heats of solution is heat enthalpy of hydration, delta H of hydration. And what this amounts to is the energy of expanding the solvent and forming the solution. So if you can imagine, you have delta H of, lost my mind, lattice energy, and then you have delta H of hydration. You add those two together, and then you have the solution. Okay, and that's expressed here. So you have the heat of the solvent and the mix together to form heat of hydration. The enthalpy of hydration is more negative for small ions and highly charged ions. This is just one other way things tend to be looked at. This graphic down below shows you that. So we have right here lattice energy. Okay, and then here we have our enthalpy of hydration, which again is our enthalpy of the solvent expanding and our enthalpy of the mix together. And overall, that's going to be an exothermic value. It has to be. And then the difference between the lattice energy and the enthalpy of hydration will be our delta H of solution. It's just another way to look at it. Okay. So it states here enthalpy of hydration is more negative for small ions and highly charged ions. This is a function of charge density. It's also expressed well in Coulombic attractions, Coulomb's formula and Coulombic attraction. Talk one little bit more about heats of solution. Generally speaking, most heats of solution are positive or endothermic. We can come up with a couple of good examples where they're exothermic though, so know that both happen. The reason the solute dissolves is that there's a solution process usually increasing in entropy. When you have an endothermic process, you think about this formula here. So you think about this all the time. Remember this guy? Well, you've got two things to decide whether or not this process is going to be thermodynamically favorable or not, right? We have the delta H. If that's endothermic, that's kind of one strike against us. That means our entropy change must be so great that whatever temperature you're working at, you have a delta G that is negative. So because most heats of solution are positive or slightly positive, the reason that that solute dissolves readily in solution is because of this increase in entropy. So please have that process in mind when considering solutions dissolving. Again, solution process involves two factors, the change of heat and the change in entropy, and the relative values determine whether a solute dissolves in a solvent. And this is essentially explaining delta G and ways we can make it negative. Remember, a negative delta G means thermodynamically favorable process that will happen on its own. Solubility facts. I want you to remember that phrase like, dissolve, like, and I want you to never use it again. You can think about it, but don't use it. It's generally just an observation. It doesn't really justify the behavior or why a process takes place. We need to think about things thermodynamically, and also we can use a statement like the following to make sure we're explaining with useful words. Substances with similar types of intermolecular forces tend to interact with and dissolve into each other. That's a justification of a tendency. It doesn't explain energy. If you're given information or values when you're questioned about why something dissolves in something else, you need to use a thermodynamic argument. Okay, more solubility facts. Water dissolves many salts because of the strong ion dipole attractions that water forms with the ions. They're very similar to the strong attraction between the ions themselves in terms of energy. The same salts are insoluble in hexane, which is a nonpolar solvent, because weak LDF forces of their ions could form with this nonpolar solvent are much weaker than the attraction between ions. In other words, any release of energy that might be if you mixed hexane with an ion would be significantly smaller than that would be for water. Oil does not dissolve in water because the LDF dipole forces between oil and water are much weaker than the hydrogen bonding between molecules of water. Look at that, water molecules of water from the Department of Redundancy Department. Solubility of alcohols in water. So as hydrocarbon portion of alcohols increase in length, the alcohol becomes less soluble in water. Let's show that. If we're dealing with, let's just say methanol. One carbon length. This is a very volatile organic compound. It forms vapors readily. It is a liquid at room temperature. It's also water soluble because of this nice oxygen hydrogen end. Okay, very polar on that end. If you expand that out to just say we have C16 and then at the end a hydroxide. Okay. Yes, it's still an alcohol on this end, but the length of this carbon chain, let me just draw it out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then OH. This substance At room temperature here on Earth is a waxy, flaky mess. It's called cetyl alcohol. It does not dissolve in water. It does attract to water because of this little guy on the end, but in the grand scheme, what you get is a whole bunch of LDFs that form between long carbon chains of this molecule and the neighboring molecule. And therefore, any measure of attraction to water on the hydroxyl end is minuscule when compared to the LDF and attractive forces. So cetyl alcohol is wax. So as you increase the length of the carbon chain in alcohols, what you find is you get less and less solubility in water and more solubility in something that's nonpolar like hexane. Interesting stuff. So let's talk about the factors that affect solubility. These are things we know already, but we're going to go through them. Let's talk about molecular structure. We're not actually going to know these structures, but first it's kind of familiar to talk about vitamins. So fat-soluble vitamins like A, D, E, and K, those are your fat solubles, are nonpolar, and they are stored in body tissue. That's why you don't want to overdose on vitamin A. It's great for you, eat your carrots and all, but don't go overdosing on vitamin A. It can actually be toxic at large enough doses. Water-soluble vitamins like vitamin B and vitamin C are polar. Body doesn't store them, pump through. Your body takes what it needs, excretes the rest. So these are things that determine solubility. So fat-soluble vitamins need fat to dissolve. Water-soluble vitamins need water to dissolve. Couple of terms that matter, they're hydrophobic, which means they're water-fearing. They're not really phobic. That would make them people. Nonpolar, and then hydrophilic substances are typically polar. Pressure effects. The solubility of a gas is higher with increased pressure. Pressure has very little effect on the solubility of liquids or solids. So pressure really matters in gases. Henry's law is a law that states that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. Okay? Henry's law is obeyed best for dilute solutions of gases that don't dissociate or react with the solvent. And that's kind of obvious. But you have to keep in mind that we're thinking about how much gas we can dissolve in the solution. And my immediate go-to example is the soda bottle. If you want more carbon dioxide to dissolve into the solution you've got, water, then you need greater pressure above. Here you go. So if you look at example 1, you see a certain number of particles here, and you see a certain pressure. Well, if we increase the downward pressure, we see that more of these particles are able to dissolve in solution. And then we reach this dynamic equilibrium where the two solutions, or the two processes, are in concert with equal rates. So Henry's law basically says that the amount you dissolve here is dependent on the pressure here. Great law, Henry. Temperature. The amount of solute that will dissolve in a certain temperature depends on the heat of solution of the solute. Thus, increasing temperature may increase or decrease the solubility of a salt. So, increasing temperature does not always increase solubility. Solubility generally increases with temperature. Generally. See that? If the solution is endothermic. Solubility generally decreases with temperature if the solution process is exothermic. Potassium hydroxide, sodium hydroxide, and sodium sulfate are 3 compounds that become less soluble as temperature rises. This can be explained by Le Chatelier's principle. So when we make sodium hydroxide solutions at the school, we start with cool solutions and we stir a lot because unfortunately, since it's an exothermic dissolution, as the solution heats up, it becomes a challenge to continue to dissolve the sodium hydroxide. So you have to have time for the substance to cool. So with gases, the solubility of a gas in a liquid always decreases with increasing temperature. This is an always. Gases increase temperature, decrease solubility of gases in water. And this actually spills into the whole notion of thermal pollution in energy. Energy companies use water often to cool things, and water as a coolant is fantastic. It takes on lots of excess energy and can help keep process where there's lots of friction from overheating. The problem is where do we put that hot water once it comes out of the system? And sometimes it gets dropped in a local waterway, and those local waterways contain living animals and organisms and systems, and that increasing energy into the water may just take the temperature of the whole body of water up 1 or 2 degrees, but such activity has been known to kill off entire populations of animals. So, important to note that. Oh, why did it kill the animals? Because dissolved oxygen in the water decreased, which changed the ability of the animal to get and use oxygen, and then they die. And this is the classic solubility temperature graphic we're used to from introductory chemistry, and we note the units always. These units are huge. When you're given a graph, the first thing you should look at is the units. Generally, what we see in solubility curves are the mass of solute soluble in 100 grams or 100 milliliters of water at a given temperature. And note your aberrations, your sodium sulfate and your cerium sulfate decrease solubility with increasing temperature, and those are solids, not gases. So changing vapor pressure. While the presence of a volatile solute, more volatile than the solvent, increases the vapor pressure of a solution, a non-volatile solute lowers the vapor pressure of the solution. So this is a function of what's being put into the system. It's kind of an obvious. This is because the dissolved non-volatile solute decreases the number of solvent molecules per unit volume. Therefore, there are fewer solvent molecules on the surface of the system to escape. Okay, there's a law for this. I'm going to spell it. Raoult's law. Not much to memorize here. You certainly don't need to know Mr. Raoult's name, but this is a principle that you can manipulate the volatility of a solution by adding another solvent, a solute, to the solution that's less volatile. So imagine if you take water with acetone. Acetone is quite volatile at room temperature. If you add water to this acetone mixture, or to the acetone and form a mixture, then you find that the overall volatility of the system is decreased and less acetone is able to escape because of the mixture with water. Here's a cool picture. This is in a bubble. If you isolate a system where there are solvent particles and then solute particles nearby, you can actually get the water molecules to leave this system and dilute this system over here. Very cool. Takes time. Here is another graphic showing the same thing. So now let's look at liquid solutions. Liquid solutions in which both solute and solvent are liquid, and the liquids are volatile. They do not behave ideally. Both solute and solvent contribute to the vapor pressure of the system. If the solute is more volatile than the solvent, the vapor pressure of the solution is higher than the vapor pressure of just the solvent. So here we go. Two vapor pressures, and they're additive. Very interesting stuff. Colloids. Colloids are also called colloidal dispersions. They are a suspension of tiny particles in some medium of any phase. You can have solid gas, liquid solid, etc. The dispersed colloidal particles are larger than the simple molecule, but small enough to remain distributed and not settle out of the system. A colloidal particle has a diameter between 1 and 1,000 nanometers and may contain many atoms, ions, or molecules. Because of their small particle size, colloids have an enormous total surface area. Foams, aerosols, emulsions, sols are various types of colloidal dispersions. Nothing to memorize here. These are just facts that we need to understand. Why do the particles in the colloid stay suspended? Why don't they fall out of solution? Generally, it's because of electrostatic attraction or repulsion. Okay, you can coagulate a colloid by heating, increasing the collision speed of the particles, or by adding an electrolyte. Electrolytes neutralize ion layers. We can often separate particles in a colloid by filtration. There's the example again. Colloids tend to show what's called the Tyndall effect. And the Tyndall effect basically is particles within the solution or within the colloidal dispersion reflect light, and then the light particles bounce off of them. It's used to help us distinguish between a suspension and a true solution. A true solution has particles that are too small to scatter light, for example, plain old ions. So this, in the diagram, the picture you see here is a great example. You see you have clear water here probably, and the laser passes through, and you don't see the laser line, but the next solution is a colloid, and you can very visibly see the laser line. The laser line indicates the laser is bouncing off large particles in the solution, and therefore it is a colloid. Finally, Brownian motion. My graphic's not going to play. That's a bummer. But what it is what you see in this is, imagine you've got a slide preparation under a microscope, and you have what appears to be a particle just randomly moving through a solution, just moving all on its own like it's alive, but you know it's not alive. Like, for example, you're looking at a blood smear and it's a platelet, and the platelet is just creeping along underneath a slide. It shouldn't be moving. You might think, oh, it's the wind. It's not the wind. Keep in mind that inside a solution are quadrillions of water particles and other small particles that are moving at whatever kinetic energy they have. And they are moving about at random, bouncing off of each other. They're also bouncing off the particle you can see with your eyes. But they are large enough to collectively have an impact on the motion of the particle. That's called Brownian motion. The collisions between visible colloid particles and invisible solvent molecules, they cause the motion, and we will look at that graphic in class because it's super cool. That concludes our discussion on the chapter 11 up to 11.4 on salt and solution properties, and we'll see you in class.